Swayam Prabha. Digital India. Educated India.
Now, of course, we would like to have an expression for something like this, and that we can get by solving this. We'll do this in many different ways. I know that this is very simple and many of you probably already know the solution, but we will use this so often that it should become automatic. If you look at a circuit, you should be able to tell what's going on and why it is that way and so on. Okay. So that's why we'll spend a lot more time on this than we would in mathematics class on a first order differential equation. Okay. By the way, this kind of thing is known as this is a first order differential equation. Why is it called first order? Because differential equation is nothing but on the left hand side you have the variable itself, Vc in this case, and derivatives of the variable, and you can have higher and higher order derivatives. So the order is defined by the highest order derivative that's there on the left hand side. On the right hand side you group all the constants which are sort of inputs to the system. Okay. And this one which has 0 on the right hand side, what is this? It's called a homogeneous differential equation. Okay. So in general, if you have only variables and 0 on the right hand side, that's called a homogeneous equation, right? So if I rearrange this now, I get okay. So now we have this expression which says that the derivative of some variable Vc is some constant minus 1 by Rc times the same variable. Okay. Now this is the kind of differential equation you could have solved maybe 5 minutes after learning about differentiation, because you are given the table of different derivatives and you see which is the same on the left and right side on the table. That's the solution, right? What is that? This is usually the form in which it is put. So what is the solution to this? Y equals exponential alpha y, yeah. What is it? Exponential of alpha x. Okay. So the derivative of an exponential is an exponential. Okay. So that's actually a very significant thing. So the solution to this, as all of you easily guessed, is now there has to be some constant here, right? This is of the form of exponential minus t by Rc, but there will be some constant, because if you multiply, if you scale Vc by any number, that's also a solution, right? This is, by the way, this kind of I forgot to mention that particular term. So this is not just a first order differential equation, this is a first order linear differential equation. Okay, because we have Vc and the derivatives of Vc, but we don't have squares of Vc or squares of the derivatives, etc., etc. Okay. So this also means that because it's a linear differential equation, if you have a particular solution Vc of t, then some k times Vc of t is also a solution, right? Because all of these terms will get multiplied by the same k. Okay. So Vc will be of the form Vc naught exponential minus t by Rc, and so if I take my example of Rc with an initial voltage of 5 volts, okay, and in general this is always true because you are solving for linear differential equations. When you solve for a homogeneous linear differential equation, the result you can get it, but it will be ambiguous by some factor, okay, because you multiply the solution by any factor, that's also a solution. Okay, so how do you tell what this factor is? So that is done based on the initial condition. So you should be given initial conditions when you solve for a differential equation, and based on the initial condition you can find these constants. Now in case of a first order differential equation, you will have one such constant. If you have a second order differential equation, two such constants, and so on. Okay, so the number of initial conditions has to be equal to the order of the differential equation. Okay, in this case it's very obvious. What is the value of VC0? So in general, you will find it by substituting some suitable value of t, for which you already know the solution. In this case, you know that for t equal to 0, the solution is 5 volts. Okay, so that means that VC0 is 5 volts. Okay, this you get from the value of t equal to 0. So you start with 5 volts and does that. Okay, this curve is 5 volts exponential minus t by RC. Okay, and this is Vc of t. Now before, I didn't want to just solve for this and plot it, because sometimes then you can lose the feel for why it is the way it is. We earlier solved it sort of graphically. We have 5 volts and minus 5 volts by R through the capacitor, and that will reduce the voltage. As the voltage reduces, the current reduces, so the rate of change keeps on falling. Okay, so this business of the rate of change being proportional to the function itself, that's what gives you an exponential. Okay, in this case, the rate of change is proportional but with a negative sign. So that's why what happens is it starts falling, and then the rate of falling becomes shallower and shallower until finally it reaches 0, but only at t equal to infinity. Okay, that's known as asymptotically reaching some value. That is, it won't reach that 0 value for any finite value of t, but only for t equal to infinity. Okay. So you should know both these, like how to solve for this is after all a very simple equation. At the same time, why it comes out the way it is, that you know from the circuit, that the current in the capacitor keeps on falling. Okay. Now, what is the initial slope of this? What is dVc by dt? Minus Vc naught by Rc exponential minus t by Rc. Okay. So again, if you look at the value of t equal to 0, it is Vc naught by Rc, right? That we could tell also by just looking at the circuit, because we have 5 volts across the capacitor, which is also across the resistor. Okay. So the current is 5 volts by R, and the rate of change of voltage is I by C, okay, which is 5 volts by Rc. That is the rate of fall, and then that keeps on reducing. This is fine. Okay. And this quantity Rc here, like we'll see later that we'll do more calculations of this circuit, and that thing appears all over the place. Okay. So this exponential will have minus t by some quantity that has dimensions of time. Okay. So this is known as the time constant. Okay. And that comes about because when you write the homogeneous differential equation like this, the coefficient is over there. Okay, you have minus 1 by Rc. That's what makes this Rc go into this exponential, right? So that's a characteristic of the solution to this differential equation. That's the time constant. And it's very common to hear the terms like Rc time constant of a circuit. So this is what it is. Okay, so it influences the rate at which this falls. What happens if this time constant is very large? What happens to this curve? Will it fall quickly or slowly? Slowly, right? So because if let's say R is very large, I mean the time constant could be very large by the R being very large or C being very large. If R is very large, what it means is that the current is very small. Okay, initially for the same 5 volts, the current is much smaller. So that means that it will discharge the capacitor lesser. After all, what is happening? Initially you have some charge across the capacitor that is leaking through this R, and then goes all the way to 0. Now if the resistance is very large, then it means that very little charge is taken out per unit time, so it discharges very slowly. Alternatively, the time constant can be very large by the capacitor being very large. So that means that it has so much charge that if you take a certain amount of current out of it, the reduction in voltage is much smaller. Okay. So these are all just intuitive explanations for what comes out algebraically very easily. Okay, and it's also quite important to realize these things intuitively. So this is a circuit with a long time constant, and you could have a very short RC and then it will do something like that. And this is a circuit with a very short time constant. And depending on the application, you may want a long or short time constant. Okay.